Alright, so this is our, I guess, new last video for Chapter 4 for Math 1560, Calc 1 at U of L for fall 2017. I decided to split up the last video because the length of the video got a little bit too long. We were sitting at about 26 minutes. That seemed like a bit much, so I cut the last couple of examples off of that video. Let the first part of that one stand alone, and we're going to re-record these last examples. So what we're going to do now is we're going to use that remainder formula that we talked about in the previous video to get some estimates on the error. And what we want to do here is we want to, in this case, what we're looking at is somebody is going to tell us the error. They're going to say we want to make sure that the error is no bigger than this amount, and it's our job to figure out how many terms we need to take in our tailored polynomial to satisfy that condition. Okay, so here's a typical example. We'll do the sign 1 part first. We'll come back to sign 2. So we want to find the least integer n such that the degree n Maclaurin polynomial for the sine function gives us the value of sine of 1 with an accuracy of 7 decimal places, right? So the idea here is that sine of 1, right, we can approximate sine of 1, so by the degree n tailored polynomial, right, for some n, and the error in doing so is given by the absolute value of the remainder at 1. Okay, so let's remind ourselves, what does that remainder look like? So the remainder formula was this. This is Lagrange's formula for the remainder. We do n plus 1 derivatives. We evaluate at some number c. We multiply by x minus a to the n plus 1. We divide by n plus 1 factorial. And we know that c is some number between a and x. And for us, we're doing Maclaurin, so a is equal to 0. We're setting x equal to 1. And so in this case, we know that our error is given by this value. It's given by the absolute value of the n plus first derivative of f at c. When we put in a equals 0, x equals 1, we're just going to get 1 to the n plus 1. I mean, we could put it in, right? But 1 to the n plus 1 is still just 1 over n plus 1 factorial. And what do we know about these derivatives? Well, all the derivatives of sine are either plus or minus sine or plus or minus cosine, right? The derivatives go sine, cos, minus cos, then back to sine, and then it repeats. Now, we don't know what this number c is. We know it's some number between 0 and 1, but that's all we really know. This remainder formula is obtained using a version of the mean value theorem, and we know that the mean value theorem never tells us what this number c is. It gives us some interval where we know we can find it, but that's about all we know. But when we're trying to kind of estimate our error, kind of manage our error, we just want to make sure that error can't get too big. And so if we can get an upper bound on the error, if we can get a number that we know is bigger than the true error, and we can make that bigger number small enough, well, then we're happy. And so what we do here is we say, hey, we know that sine and cos both have range from minus 1 to 1, so that absolute value has some value somewhere between 0 and 1. Worst case scenario, the value of this derivative is 1, right? So this error is got to be less than or equal to 1 over n plus 1 factorial, and we want our error to be less than, well, we want 7 decimal places. So that means we want 0, 1, 2, 3, 4, 5, 6, 7. And we need to make sure that the digit in that 8th decimal place is less than 5, right? So we want an error less than that, because if that 8th digit is 5 or more, we might get a rounding error, right? So this, if we want to kind of write this in scientific notation, more compactly, we can write this as 5 times 10 to the minus 8. Okay, so how do we calculate that error? Well, the easiest way, I think, to kind of see it is in a spreadsheet. You can also do even a basic calculator. You can do it, right? Because notice that what we're doing is we're dividing by a factorial, and we know that a factorial is just a product of integers, so we can divide by 1 and then take that result, divide by 2, then divide by 3, then divide by 4, then divide by 5, and just kind of keep dividing by the next number until you get something that's small enough. The only problem is if you're using a cheap calculator, you maybe can't display more than 8 digits, and so you can go to a scientific calculator, or we can go to something like an Excel spreadsheet. So what I've done here, we've got things set up for the next part of the question there as well. We want to calculate 1 over n plus 1 factorial. So column C has my n value. This is C2. So n is equal to 1 is C2 equals 1. So I want to add 1 to that and then do the factorial. So you'll see that in the function here, C2 plus 1. Take the factorial and then do 1 over that number. It gives me 0.5. So I can take that formula, I can copy and paste down to the next few cells here, right? And it's gonna execute that formula for n equals 2, 3, 4, 5, all the way up to 9. So we get to n equals 9, and we see, okay, what do we got there? 2.7 times 10 to the minus 7, but we said that we needed 10 to the minus 8. So let's go to the next one. There we go. So n equals 10 does the job, right? When n equals 10, I find that my remainder can't be any bigger than 2.5 times 10 to the minus 8. So that does my job. So if we go back, we find that the absolute value of R10 of 1 has to be less than or equal to 2.5 times 10 to the minus 8. So this seems to suggest that n equals 10. Now, if you want to, you can be a little bit clever here. If you're paying attention, you might say, "Hey, wait a second! I remember what the tailored polynomial for sine looks like. The Maclaurin polynomial for sine. We know that P10 looks like this. It looks like x minus x cubed over 3 factorial, x to the 5 over 5 factorial, x to the 7 over 7 factorial, x to the 9 over 9 factorial. Only odd degree terms show up, right? The coefficient for x to the 10 is 0. There is no x to the 10 term, right? So P10 is actually the same as P9, and what that tells us is that n equals 9 will do. Now, if you're doing the online homework, you're working on homework 10. The last question there is a very similar question to this one. You're going to find another one like this in the textbook using cosine instead of sine. Between this video and the textbook, you should have that one covered. If you look at that question, you'll find that in one of the two cases you'll probably be in this situation where you can actually go down by a degree if you pay attention to what the tailored polynomial looks like. The computer will actually accept either answer. So if this was what you were given on that question, both 9 and 10 would be an acceptable answer. The computer will take either one, just in case you were wondering. Now, what about when we go to sine of 2? So for sine of 2, well, we can do the same sort of thing. The remainder at 2, that 1 to the n plus 1 is going to become a 2 to the n plus 1 over n plus 1 factorial. And so that 2 to the n plus 1, right, that's going to grow, right, well, exponentially. It's an exponential. But exponentials, fortunately, don't grow as fast as factorials, and so we'll still be able to get the error down far enough. And we can look in our spreadsheet. I set this one up as well. Okay, so you can see if you look at the formula, it's 2 to the power I2 plus 1. I2 is my n this time, over the factorial of I2 plus 1. So that's the formula we want for the remainder. And this time, if you copy down up to 9, well, we can see that by the time you get to degree 9, degree 9 was good enough for sine of 1, but it's not good enough for sine of 2. It only gives us the first 3 decimal places, and we wanted 7. Okay, so if we want to get more decimal places, we're going to have to go to a higher degree. So we tried 10. That gives us 4 decimal places, maybe 11, 12, not there yet, 13. Well, now we've got 10 to the minus 7, but that's still affecting that 7th decimal place, so we got to keep going. 14, there we go, 10 to the minus 8, 2.5 times 10 to the minus 8. So again, we find that this is less than 5 times 10 to the minus 8 for n is equal to 14. And again, because only odd powers show up in my tailored polynomials, n equals 13 will do. Okay, so these are a couple of examples where things are actually quite manageable. Even going up to degree 13 isn't so bad, right? I mean, this is something you can easily get a computer to do. What if you wanted to use tailored polynomials to approximate the value of the natural log? Something like log of 2. That's something you might ask for. How many terms would we have to do here? Well, you can work out what the tailored polynomial is for log x centered at a equals 1, and what you find is you get this: a plus 1, or sorry, x plus 1, then x plus 1 squared over 2, x plus 1 cubed over 3, and so on. The last term is going to be minus 1 to the n minus 1, x plus 1 to the n over n. Okay? The remainder in this case, we get n plus 1 derivatives at c over n plus 1 factorial, and we're expanding about 1s, so it's x minus 1 to the n plus 1. And you can work out with a bit of work. I'm not going to do it here because I don't want this video to get too long. It's long enough already. This derivative turns out to be minus 1 to the n times n factorial over c to the n plus 1. So if you plug that in and you clean it up, then what you get is this. You get minus 1 to the n, x minus 1 to the n plus 1. N factorial divided by n plus 1 factorial. N plus 1 factorial is n plus 1 times n factorial, right? Because we're multiplying the first n integers together, and then we're multiplying by the next one. So we can split it up like that, and then that lets us simplify, right? N factorial over n plus 1 factorial is simply n plus 1. And then we have this c to the n plus 1. Okay? So for x equals 2, which is what we're interested in, right? We're interested in log 2. We know that c has to be somewhere between 1 and 2. Okay, and so the remainder, and also, well, 2 minus 1 to the n plus 1 is simply 1. So the absolute value of our remainder, well, the absolute value is going to destroy that minus 1 if it's there. And then 1 to the n plus 1, just 1. We get 1 over n plus 1 times c to the n plus 1. And again, we're worried about the worst case scenario here. What's the biggest the remainder can be? Well, we get the biggest possible value out of that remainder if c is as small as possible. So if c is 1, we're there, right? We don't want to assume that c is close to 2 and discover that we underestimated our error. And we want this to be we want accuracy up to 3 decimal places. So we want this to be less than 0.0005. And if you work this out, put it in a calculator, you'll find that this means we need n to be bigger than 1,999, which is pretty big, right? We'd have to take like 2,000 terms in our polynomial to get just 3 decimal places of accuracy for the log function. So that's a lot more challenging than what we saw with sine, or what you might see with cosine or the exponential function, right? Convergence is much slower for the natural log. Okay, that now is it for chapter 4, and we'll be putting up some videos from chapter 5 pretty soon.